we are gladly, we will have Nathalie Wahl from University of Copenhagen to tell us computing string topology operators.
Yes, thank you, Gushan, for the introduction. So yes, so I want to talk about computing string topology operations. I'll try to do actual implementations. In sort of a geometric definition of string topology. So I'm going to have M for a closed oriented manifold, and for convenience, I'm going to become metric. And again, so when we have the loop space, which is ordered out from this S1 into N. And so Chas and Sullivan defines string operations. Maybe the main ideas would be to take it as a product. When you look at, you have a pair of loops, you would like to multiply them by somehow concatenating them. You cannot quite do this for loops that don't share the same base point. So what you do is you somehow intersect with this subspace of the loop space where the loops have a base points agree on the base point, and then once you have such loops, you can concatenate them. And then maybe you could also do this starting with a single loop, reinterpreting the same image by saying, well, this is now self-intersecting loops. So if I have a loop and it happens to self-intersect, then so I'm thinking of this as a loop that path is from 0 at some other point, and then I could cut it and get two loops. So the very same picture can be interpreted into different. You can also try to define some intersection map that goes from this bigger space to the subspace and get an operation in homology. Okay, so what I want to do for the talk is to actually define these two operations somewhat more precisely, and then start computing, do some computation. So I mean, see how far we get, but at least give some idea of how these things work out. And but maybe for people who missed the first talk and for people who fell asleep during the first part of the pre-talk, so what are sort of good things to know about string topology before we start computing it? Well, one thing I tried to say was there exist lots of string topology operations. So I'm mentioning two now, but there are tons. Okay, so these are the first. In fact, I'll just talk about two, but there are many more. They can be useful string topology operations. I mentioned a couple of applications to detecting homology classes in things like moduli spaces of Riemann surfaces, or saying something about geodesics. And there are also fun applications to the homology of Lie groups and things like that. And then another thing I will not talk about is Hochschild homology models. So you can go algebraic. I'm going to stay geometric and do things geometrically. You could go completely different and also do computations algebraically where it's more combinatorial. And you do also get, I mean, there are also things that you can actually do. Okay, so these are the things that I will not not say again. Okay, so what, how do we define these operations? We need to do some sort of intersection from a big space to a subspace, and what we want to do is to lift the intersection product of a manifold. So we want to lift the intersection product And you know what we do is we pick the data. We have n cross n. Our diagonal, we're going to pick the data of a tubular neighborhood. Which comes also with a retraction, so it's homotopy equivalent to n sitting here as a diagonal, and then we pick a term class. A term class for this neighborhood. Now this data is enough to define the intersection product. So you go relative to a complement of your diagonal. You go you use excision to go to the subspace defined by the neighborhood, and then you can get out with your examples. And that takes you back into becomes a non-relative homology class. You lose some degree, and this is now isomorphic to the homology of F. And so to live to the loop space, to do these two operations, what we do for the product, we look at ln cross ln, we evaluate and zero those loops into n cross n, and then we can just define the similar. We can just pull back everything. So this is a space of points that are close to one another. Then we can look at the inverse image here, which is a space of loops that have basically the same evaluation at zero. And we can pull back this term class along the very same map. It will be by pulling it back, it will give a class in this neighborhood that vanishes away from the inverse image of this, which is, I mean, this is the diagonal, this is the loops where they agree. So that is, you know, the complements of the loops of these figure eights spaces, whether they respond to the complement of the inverse image of the diagonal. So the data we used to define and from this neighborhood, so from what is the data we used? We used a certain subspace that had a retraction back to M. So we would like this to also have a retraction back to, doesn't matter that it's an equivalence, to Lm crossover M Lm. So these are loops that almost self-intersect, and these are loops that actually intersect, and they almost intersect. You can add a little geodesic and make them actually intersect. You could push if you prefer. So we have a map like this. We have a class that vanishes away from our subspace. Now it's like it's a huge space, and we have some subspace, and we have a class that vanishes away from that subspace. So formally, we have sort of the same data by just putting it back. And so you can just do the same. We can do the same definition. Ln cross Ln, and then we go relative to a complement of our subspace. We use excision to go into this neighborhood, and then we count with the term class, and then this pull back to the class, and it will land us to the homology of the neighborhood, which we can then rewrite the homology. of the loop space. So this is sort of, so this is how you can formally define a product. If you maybe let me also say a few words about the coproduct. We want to talk about it also. So for the coproduct, I said, well, you could consider the same picture as being self-intersecting loop here. The sort of the first guess you might take, you could coproduct. What did I do? I started with my original space, which now would be LM, a single loop, and I want some sort of evaluation map to M plus M if I want to pull something back from here. And the first thing you might try is to say, I evaluate at 0 and 1/2. Okay, that's a legal thing to do. I can do exactly what I did there. I pull back my neighborhood, my class, and everything. Yeah, I have, I have loops that almost intersect, and then I add a geodesic, and then I can cut. If I go to two loops that actually intersect, then I can cut and I get two loops. So we get the product, the two products, and then to the homology of these self-intersecting loops. As before, LM cross over LM, and then I can. I've lost n in degree because I do again. I'm capping with a ton class again. I'm doing an intersection. So if I do this, I get a trivial. This gives a trivial coproduct. It's not exactly trivial, but it's very close to being trivial. So you have to be a little careful when you define operations, but there might be a zero operation. And the reason it is trivial is because, well, if I use the evaluation at 0 and 1/2, it's really quite close to using the evaluation that's 0 and 0, right? It's also very close to evaluation at 0 and 1, if you like. I can let this time coordinate vary from being 0 to being 1. And now this is looking for self-intersections that always happen and creating a loop, which if I cut my cut map, which took left part and right part, here it's going to take a trivial loop on the left. Whereas on the other side, I'm going to do a trivial self-intersection, and I'm going to take a trivial loop, a constant loop on the right. So these will, if you put these two facts together, it will somehow, we will say that it can only be non-trivial on constant loops, and only because of the degree, it can only do something non-trivial on the fundamental class of your manifold. So it's a very, very limited thing. It multiplies the fundamental class by the Euler characteristic. That's what it does. Okay, but homotopy theorists know that when you have a trivial operations that is trivial for two reasons, then there is a secondary operation. Okay, and so this is the correct thing to do, is to use this secondary operation. Here it's the operation that says, well, you should really take all of this into account as a relative thing from this one to that one. And this is the good coproduct. And so that's what it's in some sense it has it's a one parameter operation, and it will come from the same. You can get it in the same way as before, but by looking now at the evaluation, you should take the loop space cross an interval, and you look at the evaluation at 0 and some time t into M plus n. And so this gives a good coproduct, which is highly non-trivial. This is what I mean by good. From the homology of LM to the homology plus 1 minus n. You have a plus 1 because it could be one operation. It's a one parameter of operations. of ln plus ln, but the sort of the natural way to define it becomes it's going to be a relative operation. And the easiest way to define it is to say it's relative to constant loops, because the boundary of the interval exists, and it was almost zero operation. It's not exactly. If it had been zero operations, it would not be relative, but it wasn't exactly zero. And so there is you're forced to do a sort of relative term. So one way to do it is just this. I mean, this one is not really necessary, but this one is. Okay, but otherwise you use this evaluation map instead of the other one, and it's the same. It's the very same thing. Yes.
So why is there
Okay, so Maxime is asking why work with the interval rather than the circle, and this is something that puzzles me. So you could also, this is totally legal. Instead of using the interval, I could use LM cross S1 and use the evaluation at 0 and t in the very same way. So this is a well-defined map, and I can play the same game as before. So in some sense, the relative term, if you write things down, I would say, okay, you take homology of LM and then you cross. Now I'm going to cross with S1 instead of crossing with the interval, and I have no boundary, no problem. H star plus 1 of LM cross S1. And I can do the same procedure as before, and I will get into H star plus 1 minus n of, the subspace of loops, the subspace of gamma t such that gamma of 0 equals gamma of t. Right? I have self-intersecting loops. I lose my cut map because I don't know what is left and right anymore. Because when my time parameter crosses back between 0 and 1, at the beginning I know who is left. I know who is left. As my time goes around, this is my left loop, and then when I pass back, it becomes the right loop. Okay, so it would naturally go, if I really want to do coproduct, it will go to, you could go to the homology of LM cross LM mod 0 2. I don't know which is, I don't know which it is. Right? It exists, I know very little about it. So it's somehow, it's in some sense a nicer operation, but I really know what was, I know almost nothing about it. Yeah, so yes. It's somehow, yeah, I don't know, this S1 is irritating when you try to work faster. And I don't know why. Okay, so that was for definition. So I promised computations. And if you want to do geometric computations, then what you want to do is to say, well, this is all based on the intersection product of the homology of the manifold. And the intersection product is called intersection product, not because it intersects with the diagonal, but because it intersects homology classes. So the sort of practice is if you have some classes like D inside M, so some manifolds that are transverse, then if you consider these as, you can consider the associated homology classes in D in the homology of M, then their intersection product is the intersection. A intersection product B is modeled by simply intersecting these two manifolds. And so if you have nice representatives of classes, this is a really easy thing to do. Okay. So what's the version of this for the string product? This is in sense I really might not want this Nancy Hingston. Is well if you have classes, now I'm in the homology of the loop space, and let me give a name to these maps. I mean, I have some classes A and B that I would like to take their string product. Okay, and how did we do the string product? We use this evaluation map at 0 to the manifold, and we did an intersection of the evaluation maps, right? So it's really something about, I mean, the intersection is happening with this composition. So this is like F0 of ZA and F0 of ZB, and so it sort of behaves as you would want to. That is, if you do the string product, A denoted like this, A B, so this is the string product of these two classes, the product of the. First take the cross product of the two classes and then apply this sequence of maps. This is simply given if assume that when now I have two maps to M, assume that A and B are manifolds, and these two maps are transverse maps. For every point in the image that comes from both places, then the tangent bundles generate the tangent bundle of the image in M. So this is something about manifolds. It has nothing to do with the loop space. You can ask for this, and if this is the case, then you can compute the string product by just take the locus of intersection. And then you just concatenate your loops where they agree on the base points. So you take like the concatenation of the loops restricted to where it makes sense. F0 plus F0 inverse of the diagonal inside equals B. Right, the pairs of points where the loops agree. This is okay. So maybe here's a simple calculation example for the intersection product. So we read the previous one. What's an example? Is just to say that the fundamental class of M is a unit. If I go back to my intersection product in the manifold, in the homology of M, if one of my classes, say A, is the fundamental class of M, is M is the identity, if the map here of M is the identity, then they are always transverse because A is like hitting the whole tangent bundle. So there's no condition. So they're necessarily transverse. And when I do the intersection, well, I'm intersecting with M, so I'm not doing anything. Okay. So a direct consequence of this is that M is a unit. Okay, so I'll do an example in the length space with length spaces where you have where we will also have I don't want to do the unit because the unit is a bit boring. You could do the unit. The same thing happens in the string product. If your class is the manifolds as constant loops, then the maps are always transverse, and the concatenation doesn't do anything. It concatenates with trivial loops, so it doesn't make a difference. But let's do something a little more fun. If we take a three-dimensional bed space, so is a Q, which is a full sphere, modular an action of P, that depends on Q. So how do you do this? You think of of the three spheres is the unit sphere and the complex plane. This is 3, which is inside, you think of it inside C2. And then you mod out by the action that says Z1, Z2 is equivalent to e to the 2 pi I over P Z1, so rotation by 1 over P for the first coordinate, and then you rotate by 2 pi I Q over P Z2. So you do a rotation by Q over P. Yes. So that's the length space. And so the length space, so we want to talk about the loop space of the length space. So I need to give you some, and if I want to do computations like this, I should give you families of loops. And so I'll give you some three-dimensional family, but we will use the following. So note, so when we define the length space, what we use is the fact that there is on C2 here, we have a torus action, which is rotate the first coordinate and rotate the second coordinate. And in that torus, we picked a Z mod P subgroup, right? But that's very little compared to the whole torus, right? So when I pick the Z mod P torus, I still have actually a whole torus action because the torus mod Z mod P is still the torus. So there is a residual S1 cross S1 action on L in Q, which takes, a Z1, Z2, let's say I take an ST inside here, it takes Z1, Z2 to e to the 2 pi I S over P V1. And then if I do this, then I have to take e to the 2 pi I Q S over P for this to be well defined, but then I can still do, I guess, plus I want to do, I guess. I think I still have a possibility of a plus T that is independent of this. That's correct. Yes. Okay. So I still have a residue this action. So now how can I define some families of loops? What you can do is to look at the following. So here's a map. So I'm going to take A to be the length space itself. I should say these are classes. We'll get to the coproduct. These are classes that Rivera and Naef defined and did computations for the coproduct. I'm going to do a product computation, but I'll get to the coproduct in a second. So the manifold I start with is the length space itself, and then I want to map to the loop space of the length space, right? So this is I'm thinking of the length space as my parameter space, and I want to give you a family of loops. And what we do, we take Z1, Z2, and we map it to the loop that goes. So I'm going to use, there are lots of these and L. So I'm going to take, this is Z and L. It's going to depend on two parameters. And what are these two parameters? It says if I have an S1, then I have a Z cross Z way of mapping S1 to S1 cross S1, which is pi 1 of S1 cross S1. Right? I can map it in this sort of slope NL loops in here, and then I can use the action I can act on my point Z1, Z2. And so this tells let's move the length space. Okay, so for every time I pick some slope loop in here, I will get a loop, and this is all in all parameterized by the length space. And this has the property which we like, which is when I evaluate, if I use my evaluation at 0 in the length space, well, what do I get? I just get the identity map, right? Because the base point of the circle is going to be going to the the identity, the guy that accesses the identity here, and so it will be based at Z1, Z2. So Z1, Z2 will be when I apply the evaluation map to Z1, Z2. Okay, but that's really good because if I want to do a computation now, if I have two of these, so now if I have, you know, my A, Z, and N, so this is my length space, right, LPQ, into the loop space of LPQ, and then I have this other class, E, M prime, N prime, also parameterized by LPQ. When I evaluate it to LPQ, I get the identity. So they are happily transverse, they're doubly transverse, they're as transverse as they can be, right? And their intersection here is just a diagonal inside LPQ cross LPQ. Okay, so here's the loop product where it's given, it's already computed. If I want the product of these two classes, Chas and Sullivan product is the M prime and prime, then this is going to be what? Well, I take the concatenation of the one class with the other class on the diagonal length space in the product here. But what is this concatenation is, you know, it's all about these loops I picked here, right? I had this loop of slope ML and the one of M prime, N prime. When I concatenate them, this is the product in my pi one. I know very well what it does. It's M plus M prime, N plus M prime. So this will give me exactly the class Z M plus M prime, N plus M prime. So we should also say, so these classes come from Rivera and Naef, and then we did some these sort of computations are in a paper I work with Florian and Manuel Rivera. Okay, but this was an easy computation. Good. Okay, so one can do one can also compute coproducts in this manner. It's a little
What? So how is your you including the length space into the free loop? How are you including like M into its free loop space? I guess like what's the definition of ZML and ZM prime L prime?
Yeah, how do we define this?
Yeah.
So whenever we have a point of the length space,
Yeah.
I need to give you a loop in the length space. Okay.
Yeah.
It's going to be based at that point. And how do I define the loop? I say, you know, it's a map. A loop is a map from S1. So I have to take what S1 does, and I'm going to take S1 diagonally into the, you know, as a loop in I'm going to pick and then pick a loop in S1 plus S1. I pick a slope ML loop in here. Now I have an action. I'm going to use this action of S1 act on Z1, Z2. So for every point in the length space, I can act on. You should sort of, you know, it's difficult to draw the length space, right? But you know, I'm picking a point, Z1, Z2, and then I have this action that says, you know, I mean, it's a two-dimensional action, right? And everything. But anyway,
so the inclusion is by the constant loop map modified by an action.
Yes, exactly. Yes.
Okay.
Yes.
Okay.
You shoot off at every point. You shoot off in a particular using this S1 cross S1 action in a particular direction.
Thank you.
So what is particularly nice is like it's in particular parameterized by a manifold, and so you can try to do concrete geometric computations as we have just done. Okay, so the coproduct in 5 minutes. 6. Okay, so now you can, I mean, yeah, you can do this. You can do this for the coproduct, and it's a little bit. The computation is a little bit less easy, but it's not so bad. So what do we, the coproduct? Remember, we take the homology of the loop space, and maybe we are investigating the homology relative to a constant loop, say, and the first thing we do is we cross with an interval. We are in NM cross I relative to NM cross the boundary union M cross I. We started in relative homology here, and then we do the same procedures as before, and we intersect and so on. And I mean, the important part is this intersect. The thing that we want to compute, which is happening from here to here, and here this is like this. We want to land in +1 minus n of loops that have a self-intersections. Self-intersecting. Let me just say it like this, and then we will touch. But this is not the important map to compute is this one. Okay, and so now you can ask, well, can I do? We had this little proposition that says we could just do the intersection. If the maps were transverse in the manifold, then we could intersect them. I mean, we have also a same statement. So basically same statement, but let me just say that why it is a little bit more sudden. You have to be more careful. So I have now a class, let's say a relative class, relative to constant loops. And so what does it, I need to, the first thing I do is I cross with an interval. So I'm interested in A cross I, I have my Z cross I, mapping into Ln cross I. And I'm, and then I take this evaluation at 0 and the time given here, time t into n cross m. And what do I want to do as an intersection? When I look at this composition, evaluation of Z cross I. And on the other hand, what do I want to intersect it with? Well, now, I mean, I could have formulated the product in the same manner, right? I mean, but it's here, I don't have two classes, I have one, and I have to intersect it with the diagonal. That is the computation I need to do. Okay, so you want to say the same thing, right? If these maps are transverse, right? If so, A is a manifold. If maybe it has A cross I, it's going to have boundary, obviously. F T of Z cross I and the diagonal delta are transverse, then you can just intersect. The problem is that this never happens. It never happens because it never happens on VA cross I union A cross DI, because if I'm on the boundary of A, I'm on constant loops, and then this evaluation lands in the diagonal because the loops are constant, and whatever T I choose, it doesn't matter. I'm always on the diagonal, so definitely I'm not transverse. And the same happens when I'm on the boundary of the interval, because the evaluation says evaluate at 0 and evaluate again at 0. It's the diagonal, right? Or evaluation at 0 and 1. Okay, so what we show is that, well, it's enough that transverse away. It's enough to stay a little bit away from this. If you sort of stay epsilon away from this, you can still define your coproduct. So you can avoid this problem. Okay, so it's a question of looking at such an intersection. And if you are now in this transverse situation, then you can do the same as before. Then the coproduct of A, so the coproduct, it will have the same type of form. So it will be cut of Z of Z of I, I don't know how to, restricted to A plus I intersect with the inverse image of the diagonal and inverse of the diagonal. So the only reasonable thing you can write. Okay. Now, when you do this for length spaces, these classes Z and N, they're not exactly transverse. So they're not actually transverse. But you can push them around again. So you first, when you do the computation, you first have to make them transverse. So you modify them a little bit, you push around, you change the parameters a little bit, until they are transverse. You can still do this, make them transverse. And once you make them transverse, then the computation becomes a count intersections. With your diagonal, so it becomes something you can. I wouldn't be able to do this on the board right now, but it is something you can do. And what do you get? Well, you will get something that depends on your parameters. Right? You start with a length space with some P's and Q's, and whether you intersect, and then you have this ML, and whether you intersect the diagonals at a particular time, then it will depend on all of these numbers. And so you get something with a lot of numbers, and then you can check, and this is where what Rivera and Naef this is. I mean, in a particular example of this, to check that these numbers depend sufficiently on PQ MLN that they know whether your length spaces are homotopy equivalent or homeomorphic. So that's the very short version of the computation. I'll stop here.
Okay. Yeah. So maybe let's first thank the speaker. Yeah. Nathalie Wahl for the great talk.
Second thanking.